So for examples 9, 10, and 11, what I'm going to do here is, make you take a pause here, look through the examples in your textbook for some guides and things like that, because they do a number of examples there, and under very different circumstances. I mean, they have certain uses of logarithms under very specific circumstances and things like that. Um, and if you were given any kind of specific circumstance, like some of the ones they present, you would tend to be given the formulas in front of you here as well, so you wouldn't be expected to necessarily know those formulas like for various circumstances. But look those over, and then what I'm going to do is present 3 problems, examples 9, 10, and 11, to you, and you're going to try them first, and then I'm going to show you how to go through and do them. So take a moment and make sure you do that before you move on with the rest of this recording. I'm going to move on with the recording, but you can pause this anytime you want. So example 9, if the original concentration of a drug in a patient's bloodstream is C, which is milligrams per liter, T hours later, after the concentration will be C of T equals lowercase c e to the negative kt, where k is the absorption constant. If the original concentration of the asthma medication theophylline, you could say I'm not familiar with the drug, so I'm probably massacring that name, C equals 20, and the absorption constant is K equals 0.23. When should the drug be readministered so that the concentration does not fall below the minimum effective concentration of 5? So take a moment, answer the question I'm going to pose to you, and then once you're done, if you calculated it, we're going to go over it. So let's go through this particular answer. So we have this function C of t equals lowercase c e to the negative kt. And they gave us some of the constants already, so I'm just going to fill those in right away. So this is 20. This is negative 0.23 to the t power. Okay, so we don't want it to fall below the minimum effective concentration of 5. The reason being is, if it falls below that amount, it's no longer doing anything. It's no longer, and some of these, a lot of drugs do have cumulative effects. You need to keep a minimum amount of it in your bloodstream for it to be effective. So, and that's how they determine, the dosage. They want to make sure it stays in your bloodstream, because if it totally leaves your bloodstream, then you have to wait for your body to get it reabsorbed again and for it to actually start working again. So what I'm going to do is I'm going to say, okay, well, how long does it actually take to get down to a concentration of 5? So I'm just going to let C of t be 5. And see how long it takes, solving for t, for this to, happen. So as I solve for t, I know I'm going to, I see what's on here. There's several things I have to get rid of. I have to get rid of this 20. I got to get rid of this exponential base e, and I got to get rid of this negative 0.23. I have to take care of them in the right order. Theoretically, there are parentheses kind of understood to be up here, and there's actually parentheses understood to more or less be here. So the thing that's furthermost on the outside is the 20. That's what needs to go first. So I'm going to divide both sides by 20 because the 20 is being multiplied. So I divide both sides by 20. I get 1/4 or 0.25, whichever way you want to write it, is negative 0.23 e to the negative 0.23 t. The next thing that has to go is the e. Now, the best way to get rid of e is to do its inverse. What I'm going to do essentially is natural log both sides. So when I natural log the left-hand side, I get the natural log of 1/4. When I natural log this side, since I have a log base e and an e right next to each other, these more or less cancel. And so the natural log of 1/4 is negative 0.23 times t. T is almost isolated. The only thing that's happening to it now is I have a multiplication of negative 0.23 attached to it, so I'm going to divide both sides by that negative 0.23. So t is going to be the natural log of 1/4 over negative 0.23. And when I use that on my calculator and carry through the calculation, I get about 6.03 hours. So after 6 hours and, a minute or so is when the concentration reaches 5. So it would be a good idea for me to probably give a dosage at least once every 6 hours so that, the concentration does not go below that 5. If I want it stays a little bit above, great, So, but I want to make sure it's enough time for it to run out of the system a little bit. So about, one dose every 6 hours. Yikes, I don't know why that happens every once in a while. One dose every 6 hours. Let's go to the next problem. The proportion of carbon-14 still present in a sample after T years is e to the negative 0.00012 T. Now, what's nice about your textbook is that they do give you, these, they already set up like the exponential for you at this point. I don't know if they're going to get to a point where you have to set up the exponential yourself. They haven't done that yet. So, because I've seen textbooks where they actually say, okay, the half-life of carbon-14 is this. If that this thing has 92.3% of its original carbon-14, how old is it? Where you had to basically come up with the exponent. You had to come up with this little formula that essentially that the amount of carbon-14 is going to be the initial amount of carbon-14 times e to the negative 0.00012 T. And you had to come up with that formula. They're kind of starting you off in that area. But you have this Shroud of Turin. It's believed to be the burial cloth of Christ. So they examine it. They see that the linen fibers contain 92.3% of their original carbon-14. Linen fibers, like anything else, basically what used to be a living organism. And living organisms breathe, like plants do breathe. So along with the carbon dioxide they breathe in, just like the amount of oxygen we breathe in, we also breathe in this carbon-14. And based off of that, we know like how much carbon-14 tends to be in our system, when we're alive, and then once we stop breathing, it's no longer going to be reintroduced to our system, so it's going to steadily decay. It's going to decay by certain percentages, over time. That's how it works. So the linen, same thing. We know how much carbon-14 it's supposed to contain whenever it was a living organism, when it was freshly, when the linen was freshly made. We know how much carbon-14 was in there, because it should be close to like whatever the plants we used to make the fabric to make the linen, was made, whenever they were just newly harvested. So, so we know that essentially, if P is this original amount of carbon-14, the final amount right now we say is about 92.3%. So it's going to have 0.923 times P as far as the amount it has now. I don't know what the original amount was, but the first thing I would have done anyway is divide it through, and they would have canceled. So I'm trying to solve this equation. For T. Now again, there are parentheses understood to be here. So I can't move the negative 0.00012 through division yet. I had to get rid of the e to essentially get rid of the grouping. So I'm going to natural log both sides. Of course, on the left-hand side, it would just cancel with the e. On this side, I have the natural log of 0.923. And then t equals the natural log of 0.923 over negative 0.00012. And when I calculate that out, it comes out to be approximately 668 years. Now, we're not like being, saying like, Christ, I'm not advocating one side or the other about who Christ was, but we do know that, based off of, what we know about his life, he was born, roughly 2018 years ago, although it's a little bit off. I think some scholars have said that he was actually born in 4 BCE, so I mean, he'd be even older than 2018. So, and even if you go with his age being 33 years, it'd still be close to about 2,000 years old if this was in fact the burial cloth of Christ. Well, this thing is only 668 years old, so it probably is not the burial cloth of Christ. So whoever made that claim was seriously mistaken. So, and that's how they can sometimes refute things through scientific evidence. So, last example you have. A bank account grows at 7% compounded continuously. That's the interest rate, 7% interest. And I did copy this from the textbook and stuff, so I should probably say it's interest. It's compounded continuously. How many years will it take to increase by 25% for the original amount? And how long will it take for the bank account to double in value? So take a moment or so and answer these two questions, and then I'll go over it. So first answer part A. And now answer part B. So let's go over this. The first thing I have to do before I get into answering any of these questions over here is I need to come up with a formula that represents this growth. Okay, which isn't that hard because, I mean, they tell us what the formula is, I mean, essentially. So we do know that we have a final amount equaling an initial amount times e to the 0.07t. And in both these instances, we're trying to solve for t. We're trying to figure out how long it takes, the amount of time it takes. So we're going to have to undo an exponential function. So again, logarithms are going to come into play. So with this, if I increase by 25%, that means that, if I start with an initial amount of p, I'm going to be adding 0.25 times p to that for a grand total of 1.25 p. So that's what my final amount is going to need to equal in this instance. Now, if you don't like using more abstract ideas like this and putting it in terms of an unknown value, you can just make up a number for what p is and then figure out what a 25% growth of that would be. Since it is percentages, I usually recommend 100, because that's what percent means. So if I started with a p value of 100, and I'm adding 25% of 100, which would be 25 over 100 times 100, I would get 125, which is pretty close to this. But let me show you how I could do either one of them. So in this kind of instance, so if I'm using 100 equals the initial amount, I could say, okay, well, 25% more is going to be 125. I'm going to have 100 here times e to the 0.07t. I would first divide both sides by 100. I would get 1.25. And I'm going to pause there. The reason why I'm going to pause there, what happens if I were to use this more abstract concept and say, okay, well, if I start with a equals p e to the 0.07t, and I'm saying a is 1.25 p, that's going to equal p e to the 0.07t. The first thing I would do is divide both sides by p, and I end up with the exact same formula I have here. So that's why the original amount really doesn't matter in problems like this. I mean, I don't have to be given one. Ultimately, when I carry through the very first operations I need to do, whatever the original amount is, its effect would cancel anyway. So now I have this equation, 1.25 equals e to the 0.07t. I would natural log both sides to get that 0.07t equals the natural log of 1.25, which means t would be the natural log of 1.25 over 0.07. And if you work that out, it's about 3.2 years. So to increase by 25% of the original amount, it would take 3.2 years. And that doesn't matter what the original amount is. You know, it would take me the same amount of time to go from $100 to $125 as it would for me to go from 100 million to 125 million. Same amount of time. Or to go from $1 to $1.25. Same amount of time. Because it's based off percentages. Now, as far as doubling goes, I'll change to a different color to keep these straight. Theoretically. There we go. If I'm doubling this, that means that my final amount A is going to be 2 times the original amount. So that means that I'm setting up the equation 2 times the original amount. Again, if you want to use actual numbers, go right ahead. You'll get to the same point I'm going to get to. Because the first thing I would do is divide by the original amount, and I would end up with 2 equals e to the 0.07t. As I continue to solve this, I would natural log both sides, so 0.07t would equal the natural log of 2. In case you don't realize, I'm also kind of using the symmetric property because I like having my variables on the left-hand side. That's just the way I was, brought to do that when I started learning algebra. So it's basically, a compulsion at this point, I guess you could say. So that means that t in this case is going to be the natural log of 2 over 0.07, which is approximately going to be 9.9 years. So to double it with a 7% interest compounded continuously, it would take about 9.9, say 10 years for it to happen. So that is the end of this last example. If you have any further questions, I'll bring them up in class. But now try your newly acquired skills on the practice problems I have following the links to these examples.